So we'll start with question 1. Now this one, pretty basic. This is one of the easier questions. So when doing mathematical induction, we need to have our basis step and our inductive step. So the basis is simply substituting n as 1. So when n is equal to 1, and remember we have our left hand side or right hand side. So when n is equal to 1, the left hand side works out to give us 1 plus 1, which is 2. The right hand side is 1 plus 3 over 2. So this is just 4 over 2, which is 2. So left hand side is equal to right hand side. Therefore, true when n is equal to 1. So now we need to make an assumption that it is also true when n is equal to k. So assume true for n is equal to k. And that is, so replacing all the n's with k, r is equal to 1, we have r plus 1 is equal to k plus 3 over 2. Alright, so we should be good up to this point. Then the last thing we need to do is show that it is true when n is equal to k plus 1, because remember, based on the principle of induction, if n is equal to 1 is true, n is equal to k is true, that means if we combine 1 and k to get the k plus 1, that must also be true. Clear?
Yes, sir.
So now we need to show true for n is equal to k plus 1. So when n is equal to k plus 1, we're going to have the sum up to k plus 1 r is equal to 1 is equal to k plus 1 times k plus 4 over 2. So this is what we actually need to prove. This would now be what we are required to prove. RTP simply means required to prove. So we see what's happening here. This is now our right hand side. So we need to prove that. Alright, so next page. So remember, this term here is up to our k term. So to get the sum up to k plus 1 for r plus 1, that's going to be the sum up to the k term when r is equal to 1 plus the k plus 1 term. And remember, the k plus 1 term is simply replacing the r here with k plus 1. So our k plus 1 term in this case would be k plus 1 plus 1. So this would be our k plus 1 term. And we know what the sum is up to the k term is just k times k plus 3 over 2. So replace that as well. So k plus 3 over 2 plus k plus 2. Alright, so we have this working with, and we need to simplify. So remember, we can get an equivalent fraction to this, so that's just 2 over 2. So this would be alright, so what are we working towards? K plus 1, k plus 4 over 2. So I guess we'd have to expand all of this and simplify. Alright, so in expanding, that's k squared plus 3k plus 2k plus 4 over 2. So that's k squared plus 5k plus 4 over 2. And then factorizing this should give us that k plus 1, k plus 4 over 2, which is what we have here. So therefore left hand side is equal to right hand side, hence by induction true. Got that? So is this what you got for this one? Is this what you got?
Yes, sir.
Okay, good. Alright, so on to the next one. So remember, this is a simple repetition of what we're doing. So we're doing the same thing over and over and over. The only difference is that the questions sometimes get a little bit more tricky, but in reality we're doing the same thing over and over. Alright, so for this one, same scenario. When n is equal to 1, left hand side would be equal to 1 plus 1 times 1 plus 2, so that's 6. Right hand side would be equal to 1 over 3 so that's 18 over 3, that's 6. So left hand side is equal to right hand side. So true when n is equal to 1. So that's our basis step. So the next thing we need to do is assume true for n is equal to k. That is, so we're simply replacing the n values here with k. So this is the sum up to k. R is equal to 1, r plus 1, r plus 2, k over 3, k squared plus 6k plus 11. Alright, so this is what we have. And then the next thing we need to do is to show true when n is equal to k plus 1. that is the sum up to k plus 1 r is equal to 1, r plus 1, r plus 2 is equal to k plus 1 over 3, k plus 1 all squared so remember, this is what we're working towards in the end. Alright, so now using the left hand side to prove this, we need to take the sum up to the k plus 1 term, and we already know the sum up to the k term, which would be this. So this is up to the k term, so we know this. So now using the left hand side would be the sum up to the k term plus the k plus 1 term. So that's k over 3 times k squared plus 6k plus 11 plus, in this case, what would the k plus 1 term be?
So is it k plus 2 times k plus 3?
Yes, because we're simply replacing the r here with k plus 1. So that would be k plus 2 times k plus 3. So obviously we need to expand, simplify to get something like this. And remember, I said that if we don't see it right away, what we could do is expand this one as well to see if we can get it to look like what we've expanded this to get. But let's see if we can simplify this to get something looking like that up there. Alright, so let's use, so that cannot be factorized using AC. Alright, so how can we do that now? Alright, so I guess we'll have to combine everything. LCM here would be 1. This would be 3. Alright, so that's what we have so far. And we can distribute and then see if we can simplify after. Alright, let's distribute. So that's k cubed plus 6k squared plus 11k plus 3k squared plus 15k plus 18. Let's see if we can go any further. Alright, so from here, let's combine our like terms. So that's k cubed plus 9k squared plus 26k plus 18 all over 3. let's factor k. Let's see if we can use long division to simplify that. 18. So let's use negative 3. So if we use negative 3, that's negative 27, 81. So this is 99. So that doesn't work. Let's use negative 1. That wouldn't work either. Let's see, negative 1, that's 27. Yeah, negative 1 would work. That's negative 1 plus 9 minus 26 plus 18. Alright, so negative 1 is a factor. So that means, well, negative 1 is a root. So that means x plus 1 is a factor. So k, well, not x, k plus 1 is a factor. So let's do long division and see what we're left with. So some of the times these are quite tedious. So k squared,
Sir?
yes.
The idea was just for the k plus one part. I just wrote that down and I got the k to the cube line. Like I just expanded everything for the k plus one part.
Up here,
Yes, sir.
right, I guess we could have expanded as well. But seeing that the k plus 1 is on the outside here, either way we'll get the same answer. We should get the same answer. So this is 8k squared plus 8k. So this is 16, sorry, 18k. So this is plus 18 and plus 18. Alright, so that cancels. So that means k squared plus 8k plus 18 would have been the other factor. So let's go to the next page. So this is equal to k plus 1 times k squared plus 8k plus 18 all over 3. And then this piece over here can it be factorized? 6 and 3. 2 and 9. Alright, so it cannot be. So I guess we can expand this piece over here, the piece in the bracket, and once we expand it we should get the same thing. So this is k squared plus 2k plus 1 plus 6k plus 6 plus 11. So this would give us k squared plus 8k plus 18. And that's the same thing. We have our k plus 1 over 3. So we got the same thing here as what we have around here. So that would mean left hand side is equal to right hand side. Therefore, by induction, true. So got that?
Yes, sir.
All right. So let's go for the other question. So this one shouldn't be bad either. All right, so remember, it's the same thing we're doing over and over. So when n is equal to 1, left hand side is equal to, which is 1, right hand side is equal to 1 squared, which is 1. So left hand side is equal to right hand side. True. So assume true for n equals k. That is so we're simply replacing the n values with k. So after that assumption, we need to show true for n equals k plus 1. And that is so remember what we're trying to prove is this right hand side here. So that's k squared plus 2k plus 1. So whenever we work out our solution, we should get this. And then we'll know that we're correct. So using left hand side, we know that up to the k term is just k squared. So this would be k squared plus, then we're replacing this r here with k plus 1. So it's 2 times k plus 1 minus 1. So this is k squared plus 2k plus 2 minus 1, which is just k squared plus 2k plus 1. That's simple. So we got our answer. Left hand side is equal to right hand side. So this is how you wish all the questions were, right?
Yes, sir.
True. All right. So the last question, which seems a bit tricky here, but let's see how we can approach it. Alright, so same concept. When n is equal to 1, our left hand side will give us our left hand side will simply be 1 over 3, which is just 1 over 3. And our right hand side will give us so this is 1 over 2 times 1 minus 1 over 3, 1 over 2 times 2 over 3, which is just 1 over 3. So left hand side is equal to right hand side. So true when n is equal to 1. So now we need to assume true when n is equal to k. So that's the next thing we need to do. Assume true when n is equal to k. So that is the sum up to k is equal to a half times alright, so this is what we're working with. Then we need to show true for n is equal to k plus 1. Alright, so let's see how we can approach this. So when n is equal to k plus 1, we will have something looking like this. K plus 1 equals 1. Right, so that's what we have. Alright, so let's see what we can do here. Let's close our bracket. So remember, we're working to get something that looks like this. Let's see if we can simplify this a bit. So this would be a half 1 minus 1. So this is what we're working towards getting. So using the left hand side, the sum up to the k term would be this. And the sum of the k plus 1 term, we're simply replacing the r here with k plus 1, so that's 3. Alright, let's see how best we can simplify this. Alright, so we can rewrite this part in the bracket, so that's a half times 1 minus 1 over 3 to the k. So we know that over on this side it's 1 over 3 to the k plus 1. Because 1 to any exponent is still 1. Alright, so this is what we have so far. So let's see how we can combine these. So if we're looking at an LCM, it's going to give us I think I'm going to distribute the half. Alright, so an LCM here would be 2 to the k plus 1. So that's 3 to the k plus 1 minus 3 plus 2. So this simplifies to give 3 to the k plus 1 minus 1 over 2 let me see what we're working towards. We're working towards getting alright, so if we factor out a half, right, let's see. So from this, what we're going to do is we're going to factor the half. So we're going to be left with 3 to the k plus 1 minus 1 over 3 to the k plus 1. Right, so after we do that, we can bring this to the numerator. So that's a half. Use square brackets. 3 to the k plus 1 minus 1. All of this is being multiplied by 3 to the negative k plus 1. So following so far?
Yes, sir.
So we're multiplying now. So if we multiply this times this, so they have the same base, so you know we're going to add the exponents, and seeing that this is the additive inverse of this, that's just going to give us 0. So this is going to be a half. So 3 0 minus 1 times 3 to the k plus 1. So this is just a half 1 minus, and this looks like what we're looking for, I believe. Yes, so if we simply write that back in the denominator, then we would get the exact structure of this. So let's write it back. So that's going to be a half 1 minus 3 over, well, 1 over 3 k plus 1. So that's our answer. So left hand side is equal to right hand side, therefore true. Alright, so any questions about this one?
No, sir.
It's just that it's lengthy, however, it's pretty manageable. Alright, so I'm going to give you one to try, and then we'll go through it, and that will be the end of today's session. Alright, so try this one. So the instructions are the same, prove by induction. So the sum. Alright, so give this one a try. Giving you 10 minutes, and then we'll take the next. Get through this one. So remember, the steps quite repetitive. So when n is equal to 1, left hand side would give us right hand side would give us so left hand side is equal to right hand side. So true for n is equal to 1. So now we make our assumption. Assume true for n is equal to k, that is, so we're simply replacing all the n values with k. So this is our up to k value. So next we need to show true for n equals k plus 1. That is, so that's k plus 1 over 2 7k plus 7. Alright, so this time we won't make the mistake of not expanding in the bracket. So let's expand the bracket first. So we have k plus 1 over 2. Inside our bracket here, that's 2k squared plus 2k times 2. So that's 4k plus 7k, that's 11k. 2 plus 7, that's 9 plus 7, that's 16. So that's what we got inside our bracket. So now when we're working this out, we intend on getting this side. So using left hand side, we know what we get up to the k term. So up to the k term, it's this thing here. That's k over 2, 2k squared plus 7k plus 7 plus k plus 1 term, we're simply replacing the r with k plus 1. So that's 3k plus 1 plus 1 k plus 1 plus 1. Simplifying this, over on this side we have 3k plus 4k plus 2. Alright, let's see, we can't use AC method to do this. That's 14, 2 and 7, no. Alright, so once again we'd have to do long division to get another factor. Alright, so here on the left hand side, simply I think we should expand on the right hand side, group them and see if we can simplify it that way. So that's 3k squared plus 6k plus 4k, 10k plus 8k. And it's 2 times 2 to give it an equivalent fraction. Alright, so now simplify further. We have 2k cubed plus 7k squared plus 6k, that's 13k squared. 7k okay, 7k plus 20k, that's 27k and 16 all over 2. So I'm guessing x plus or k plus 1 might be a factor. Let's see. So when k is equal to negative 1, this is negative 2 plus 13 minus 27 plus 16. 20 minus. Okay, so k plus 1 is a factor. So long division again. K cubed So this is what we get, and 8 times 4. So now we simply write this as k plus 1 over 2, 2k squared plus 11k plus 16, and this is what our left hand side worked out to be, and this is what we have for the right hand side, which is the exact same thing. So left hand side is equal to right hand side, hence by induction true. Right, so it's that simple. The only difficult aspect to this is expanding and simplifying. So you need to know how to factorize, how to distribute, everything like that. But these questions aren't difficult, and with practice you will definitely master this concept. So that wraps up proof or principle of mathematical induction using series.